Welcome to Quantum Chemistry of Atoms and Molecules live discussion session. Today is week 10, and Prabhu Chaudhary. I am a PMRF at IIT Bombay, Department of Chemistry. I am taking this course as a TA, and I'll try to solve a few numerical questions and um, what we are doing for the past 10 weeks. Actually, if we include this week also, then we are solving a few numerical problems, and we are trying to discuss some concept that might not be clear at the uh, live at the recorded lecture by Professor Datta. So this is our main objective is to give you solve some weekly assignments and try to clear your doubts. I hope you are, as most of them are mainly seeing these videos on YouTube, I guess. And the materials are also provided as in a PDF and also in the PPT format, and the links are shared by the NPTEL team. So today, what we'll do actually, we'll do last time um, we have closed the session with some with a derivation of this time independent perturbation for non-degenerate systems, and we have solved a few assignment 7 problems from the NPTEL website. And let me just quickly give you a overview that what we have done in the last week. So basically we have, okay, I guess my audio is not, audio is muted here. Let me, okay. So what we have done mostly is that we have uh, taken and we have mostly dealing with a small perturbation lambda h uh, to the power one ordered, and there is that h zeroth order, that is your unperturbed system, and then we are introducing a small perturbation, and due to that, if you can see, it is the wave function and energy is described in a power series of lambda. Okay, so and that is expanded throughout, and when we put that thing into the Schrodinger equation, our Schrodinger equation become modified, and from there we have discussed these three, particularly these three. A lot more can be generated, a lot more equation can be generated depending on what um, what order of what is the order of lambda is there depending on. So here we have taken only for lambda to the power 0, lambda to the power 1, and lambda to the 2, and their coefficient. From there we have got these three equation, and from there we have actually, let me give you a highlight, we have uh, derived first order correction to the energy. Okay, here it is, and also we have using this, we have not using this, but we have also highlighted, we have also got that first order correction to the wave function, that is lambda psi n 1/8. So that is what we have already done. Okay, and using this correction in the first order correction, actually we have shown that putting that value into the second order energy correction, we got this we got this um, uh, second order correction to the energy, that is lambda square by En2. And obviously we have solved a few numerical questions. Today my goal would be to solve a few numerical questions that I have shown, I think, in the previous day. First, let me write down the things we got earlier. So we'll be mostly using these things. So I'm not particularly taking lambda here. So I'm not writing the lambda, but the rest of the thing. So this is, if I write lambda, then it is first order correction of it. First order correction into the energy. Okay. So that is given by your nth state. Huh? Sign with 0. Then your perturbation, okay, small perturbation and the same state. That is for the first order correction. Then first order correction to the uh, first order correction to the wavelength. I actually forget that thing. I have to go and look it. Okay, so it would be something like there is some summation where your m will be equals to 0, means but not equals to n, and it will go towards infinity, and there will be some terms like um, check once before writing anything. I should see what I done last time. So your CM value we know sin 0 h1 and not en 0 minus 0. It will be sin m 0, not the nth. That is different. Then your perturbation, then your state, okay, that y e n naught en to the power of zeroth order minus, means it is unperturbed energy state of the nth state of the nth and mth state of energy of the nth and mth state. So I will also tell you not to mark this thing up. It will be given wherever your questions paper will be given. The questions will be given. These things will be given. So don't mark it up. So if you miss any one of the term, then you will miss the thing like sin 0. So this part is your CM. Now your second order correction to the energy, that is your lambda square. Don't forget it is in power of lambda, right? En 2. That is, there we will use this again, the summation equals 0 not equals to n to the power infinity lambda square psi m not this, for some, as I have seen this first equation, that's the second equation I just saw. That's why I remember, because there is a relationship between the both of them. If you remember what I am trying to say, 0 minus m naught, because you have to use this psi n 1th in while solving or deriving the expression for second order correction to the energy. So this is actually your uh, second order correction to the energy. Let us at least check once. Lambda square. Eh, yes, we have done a good job then. Okay, so with this equation, we'll go ahead and we'll try to solve these problems. I guess I have shared this problem with you last time, right? So the first question is from GT. Wait. So the first problem is from GTE, second edition. So the problem states that the first order perturbation theory calculates the energy of the nth excited state for a spinless particle of mass m moving in an infinite potential wall of 2L with walls at x equal to 0 and x is equal to 2L. So and the potential is given that inside that potential wall the potential is 0 and outside the wall that is infinity. That means your particle can't stay outside, it will be inside the box. But here you check the one thing that from a usual wave function, what we have done, usual system, that the box is actually we have written x is equal to 0 to L or x is equal to 0 to x is equal to A. Okay, now here the length of the box is usually is 2L here. So our unperturbed or you can say our wave function will be a little different, right? Not much different, just a factor will be added there in place of L. And then the question says that now the system is modified at the bottom by the following two perturbation. Actually, I am providing you only one of the perturbation. Another problem you can solve it yourself. For the time boundness of this class, I have chosen one and uh, I have hidden one of the uh, thing. So let's start. We'll start with the unperturbed wave function. Okay. So give me write unperturbed wave function. What we want to do, we need to calculate the energy of the nth excited state. Okay, using first order perturbation theory. So we need to calculate the see first order correction is lambda e n 1. Okay, according to how we have written our expression about the lambda. Now, in this case, actually, they want to know about EN1. How do I know? I'm just guessing because you see the lambda is already inside there and they haven't mentioned about the lambdas, what is going to be lambda. So maybe here the lambda is something different. Lambda is some other constant. Okay. So don't think that this lambda and this lambda is same. If they are same, then they want us to calculate this en1. Okay. Okay. Before that, let me draw the maybe I can draw the system once. So this is your particle in a box problem where this is your outside the box. This is your x is equal to 0. This is your x is equal to 2L. Outside the box, particle will not be there because your potential is infinite, right? So your particle will be inside there. And it has been said in overall case, in overall means from s equal to 0 to s equal to 12, there is a perturbation of Vpx, which is given by a sinusoidal perturbation is there. Okay. So before that, let me write down what is your psi n 0th. Okay. That is your root over 2 by, now I'll write 2L, right? Because your normally what we write for L, right? Now I'm writing for L dash, that is 2L. And your there is sine nth stated n by x. Now I'll write 2L instead of L because now again your L dash is 2L. So I can modify a little bit, that is 1 by L sine n by x by 2L. So this is your sin 0th. Now first order correction, not the first order correction, but this part en1, right? So that is your, we already know the expression, right? That is your sin with 0th. Then your perturbation, here perturbation is given by Vpx, and then your sin in 0, which is I'll write it in integral form. Okay, so your integral limits are 0 to 2a, right? Then there is 1 by L sine n pi x by 2L, which is itself a real function. Still, let me write the conjugate of this complex conjugate, which would be equals to itself. Then you have your lambda vpx. I'll write down the expression which is given lambda v0 sine ix by 2L, and then we have this thing again, right? 1 by L root sine n pi x by 2L dx. Okay, okay. Now maybe we can take out the constant outside. So 1 root over 1 by L, 1 by L will be 1 by L. Then we have lambda v0 as constant, right? Then here is our integral 0 to 2L. We have, we can write, so all are sine, right? Sine pi x by 2L into, we have sine square n pi x by 2L, right? Then we have our dx. What can we do here? So can we take anything in common here? Cos sine 1 minus cos square. If I take that, no. So, so we have 3 sine square thing, right? Let me give you a hint for that. What can we do here? 0 to 2L. Can we take something as common? Sine square n pi x. That is again, okay, we have one thing in our hand, right? What we usually do is, for this case also we'll do, that is, we'll take 2 in denominator, 2L, right? So we are multiplying 2 by 2L. This is as usual, this is sine pi x by 2L. Now I have taken 2L in denominator, so I'm multiplying this as 2 sine square n pi x by 2L. So it will become, right? What it will become? 2 sine square n pi x by 2L. And you already know, right? I will write it in different color, that your 2 sine square theta is 1 minus cos 2 theta, right? So I hope you can remember this, right? Cos 2 theta is your cos square theta minus sine square theta. So, and it is, so I hope you got my point here I'm trying to say. So I'll write it in different colors, so it will help you to understand that I have changed something here. So it will become 1 minus cos 2n pi x by 2n, which I can actually cut the L, which I'll do. Certainly, no, I will not because you can understand why I'm not going to do that in the next step. Okay. Now I will write. I'll go to the next page. Okay. Okay. So we have lambda v naught by 2L as common. Then we have 0 to 12. Then we have sine pi x by 12. Sine pi x by 12, right? Dx. And we have same lambda v naught by 12, 0 to 12. We have sine pi x by 12, and we have cos 2n pi x by 12 d. Okay, so we have to solve this integral. So first thing first, that see, this is all about solving the integral. Okay, to get the using the first order perturbation theory or the second order, you have to solve this thing to get the perturbed energy. Okay, so this is all about your integral skills. I hope uh, today we are at week 10. Even so, I hope that you are all familiar with these integral techniques. Like so, for the first integral, you can see lambda v naught by 2f. It will give me some cos, right? And integral of sine is actually minus. So it will be minus cos pi x by 2a from 2a to 0 to 2a, and some constant will come out, which is 2l by pi. Yeah. And for this case also lambda v0 by 2l, we will actually not solve it yet. I will still modify it. You know, right? So this is something in the form of sine A cos B, right? So you know, right, that 2 sine A cos B is sine A plus B minus sine A minus B. That is your sine A cos B plus sine B cos A minus sine A cos B. Okay, so this is plus minus sine B cos A. This will get cut and you will get back this. So we need to multiply with 2 here. So I can write 2 sine pi x by 12 cos 2n pi x by 12 dx. So it will be something lambda. First term is lambda v0 by pi minus cos. If I put 2l there, 2l cut. So we have cos. Still I will write because we have to solve the next part, right? minus minus plus cos pi into 0 by 12, and we have lambda v naught by 4L. Right now we have, it will go from 0 to 2L, and here we'll have sine a plus b, that is your pi x plus 2n pi x by 2L, that is actually 2n plus 1 pi x by 2L plus sine 2n. In this case, you will see this thing, right? Let me erase it a little bit. So actually, you can write in the same order what I was right. 1 plus 2n. Here it is 1 minus 2. Okay, pi x by 2 dx. So this is lambda v0 by pi. It is your 2L will cut, so it will be minus cos pi, which is nothing but plus minus of minus 1, right? And cos 0 is obviously 1, so it is going to give you 2, and lambda v0 by 4L. Now we can actually solve it. So first time will be 0 to 2L. So I will write it in our usual form, which we usually write 2n plus 1, right? Instead of 1 plus pi, because it is one of the integral. Then I take actually minus. I will take minus because minus plus minus. Then your lambda v naught by 4L 0 to 2L 1 minus 2n. I can write it 2n minus 1, right? Okay. If I write it as 2n minus 1, so I need to make sure that outside it is also I am taking one minus, so minus minus it will be plus. Okay. Okay. So here what we have got, this we have 2 lambda v0 by pi. Then we have lambda v0 by 4L sine. So now we'll have something here, constant, we'll write it later, but see, we'll get minus cos, right? So it will become plus. So we have cos 2n plus 1 pi x by 12, and we'll have the limit that 2L to 0, right? And the constant term we'll write now, that is 2L divided by 2n plus 1 pi. So we have lambda v0 by 4L into 2L 2n minus 1 pi. Again, it will become plus, will become minus, right? As it will give you minus cos. So it will give you cos 2n minus 1 pi x by 2L and the limit is from 12 to 0. So we already have 2 lambda v naught by pi plus, I'll cut some portion because 12 will cut, so we'll have lambda v0, then we have 2 pi 2n plus 1, so cos 2l. So when we put 12 here, so it will give us cos 2n plus 1 pi, okay, minus cos 0. Similarly, when we write it like that, lambda v0, it will be 2 pi 2n minus 1 cos 2n minus 1 pi minus cos 0. Okay, so I'll go to the next page and write the individual thing. So first we have 2 lambda v0 by pi. We have 2 lambda v0 by pi plus lambda v0 2 pi 2n plus 1. We have it here. See, cos pi, if you take n equals to 0, you are going to get cos pi. If you are going to take n is equal to 1, you are going to get cos 3 pi. Then vice versa, n equals to 2, you are going to get cos 5 pi. And in each of the case, the value is minus 1. So this is minus 1. Okay. What will happen in case of cos 2n minus 1 pi? See, when it is n equals to 0, then your cos is, so it is cos minus pi, which is minus cos pi, which is cos pi, right? Cos of minus pi is cos pi. So again it is minus 1. Then suppose n equals to 1, then it is cos pi. Cos pi is minus 1. Then again it is, if n equals to 2, then it will become cos 3 pi. And it will have an odd cos n pi where n is odd, or mn where m is odd. So again you are going to get here as minus 1. Always you are going to get it as minus 1. So this is 1, this is minus 1, minus 1, so it is minus 2. Here also you are going to get minus 2. So we'll write it in that form. Let me change my pen. So we are going to get minus 2 here, right? Similarly, we are going to have minus 2, so minus will become plus. It is lambda v0 2 pi 2n minus 1 into 2. So I'll write it in different unit. It is actually 2, right? So we can actually, you can see, we can take common 2 lambda v0 by pi. I think we can take common, and what we will get? 2 lambda v0 1 minus 1 by 4n plus 2 plus 1 by 4n minus 2. Okay. 2 lambda v0 by pi. Don't forget, we are trying to get this. So we'll take actually 16n square minus 4, okay, which is 4n square minus 4. So you will get Here 16n square minus 4 minus we will get 4n plus 2 because 4n minus 2 minus 4n plus 2. Here we are going to get 4n plus 2. So plus 2 plus 2 minus 4 is gone. Minus 4n plus 4n is gone. So we end up with lambda, so we take 32 out, 16, right? 32 lambda V naught n square, right? 16 plus 32, and we'll take 4 pi outside, and we have 4 n square minus 1. So actually, we are going to get 8 lambda b0 n square by pi 4n square minus 1. Okay, so we are going to get this expression for En 1th. So calculate the energy. So energy would be, see here, what is the energy when the system was unperturbed? So that was n square a square by 8 m 2 square because your now it is L dash, right? So it was n square a square by 8 m. Actually, it will become L square. It will become 32, right? So your modified energy is n0 plus n1th, not 0 but 0th, n square e square by 32 ml square plus 8 lambda v0 n square pi by 4 n square minus 1. Please check yourself that if I have made any mistake here. Okay, but I guess you have already understood uh, the concept what I am trying to say, right? 2 lambda v naught pi minus 2 lambda v naught by 2 pi n plus 1, and then it is okay. Okay, so this is your modified energy, right? The system. See, I am also missing that point that there should be a lambda, right? No, in this case, we are already using one lambda, so I can write maybe p, right? Where p is less than 1 using first order correction, first order perturbation theory, right? perturbation theory. Okay, let us go to the next question. So it was also from JTL. I have taken a part of this question, and the question says, consider a system whose Hamiltonian is given by this. So this is a matrix. In matrix format is given where lambda is very, very less than 1. By decomposing this Hamiltonian into H0 then H perturbed, find the eigenvalue and eigenstate of the unperturbed Hamiltonian H naught. So we can write this, right? So this is the unperturbed, this is the perturbed part, and your H is already given. So it is given as A naught 1 plus lambda, then this column there is nothing, then this is 8. See, there is a hint. You can see a diagonal matrix out of it. Can you see all? If we can decompose it in some kind of diagonal form, then our job is done. Okay, so let's see. E0 is there. We'll write 1, 0, 0, 0, 8, 0, 0, 0, 0, 3, 0, 0, 0, 0, 7 plus E0 into lambda. I am going to get another matrix, right? Which is, I will get 1 here, 0, 0, 0, 0, 0, 0, 0. So this is not going to be a diagonal matrix, as you can see. Here we have 0, 0, 0, minus 2. Here we are going to have 0, 0, minus 2, 0. As you can see, we have obtained this one diagonal and one, you can say, so this is a diagonal matrix, not a diagonal matrix, you can say. So this is actually your unperturbed Hamiltonian, and this first contains your lambda, right? So this is obviously going to be your perturbed wave function where your lambda is very, very less. So see, if this is your H naught, means the unperturbed Hamiltonian, so you know your H naught psi naught is going to give you. I'm not writing E naught because that will be a misleading E. Fine. Okay, so why I'm not writing E0, because E is the energy, okay, of the unperturbed. But not E not E0, E naught. Because you can see here from here, you see now what I'm trying to say. So now you already know that this is a 4 into 4 matrix, right? 4 into 4 matrix. So your eigenstate are actually going to be a column matrix, okay? So we have column matrix. What they are going to be? So one of them is going to be like this. I2 is going to be this is here eigen states or eigen functions. You can say whatever here. I'm going to fill it up soon. So as it is a diagonal matrix, earlier your is not. So your diagonal, so it is actually going to be like this: 0, 1, 0, 0, 0, 0, 1. Sorry, 1, 0, 0, 0, 0, 1. And now suppose your each not you know, right? It is E naught 1, 0, 8, 0, 0, 0, 0, 3, 0, 0, 0, 0, 7, right? So if now your H naught works on psi 1, you are going to get E0, 1, 0, 0, 0, 0, 8, 0, 0, 0, 0, 3, 0, 0, 0, 7, working on 1, 0. Here you are going to get actually E naught into, see, 1 into 1, and rest all the terms are going to be 0. Okay, all anything. So it is going, so for a 4 into 4 multiplied by 4 into 1, sorry, 1 into 4. No, actually, this is a 4 into 1. One call. Anyway, so here you are going to get 1 because you multiply anything by others, you are going to get 1. Okay, so it is going to be 1. So, so you can either think it like that way, and you are going to get your energy as uh, this might not be a right approach. Okay, okay, I'll write it like that. Let us not. Uh, so from here, You can understand, right, what I'm trying to do. That let me write. So this is the energy for the first state, right? So this is E1. Your E1 is going to be is your when E2 is going to be 8 is 0. Your E3 is going to be 3 is 0. And your E4 is going to be 7 is 0. So actually you if you think about your energies here, energy E, then your E1 is here, your E3 is here actually, your E4 is here, and E2. Well, just these are the just a nomenclature, so doesn't worry about that. Okay, so these are the eigenvalues. You can say energies, and these are the comparative. Uh, you can say the energies. Now another question from your so the takeaway from the previous question is that you have to break it into a diagonal matrix. Your Hamiltonian is going to be a diagonal matrix like this. If not, then it would be painful to solve, right? So I hope you will be able to do this by yourself. Now we'll go to another problem. That is a particle of charge. That is again this is a particle in a box. Yes, sorry, perturbation theory problem, and you will find it inside the example of the JTL book. Um, a particle of charge q and mass m, which is moving in a one-dimensional harmonic potential of frequency omega, is subjected to a weak electric field epsilon in the x direction. We need to find the exact expression for the energy. So you all remember a particle moving in a one-dimensional harmonic oscillator, right? One dimension, remember that? And then the particle is now charged. Charge is q and mass is m is given with a frequency of omega. And now the perturbation is in weak electric field of epsilon in the x direction. We need to find the expression of the energy. See, Hamiltonian is given. Okay. Calculate the fast. The second we have to do is calculate the fast non-zero correction to the energy, treating QEX as the perturbation and compare it with the exact result obtained in I, at the first part. And these are the things given, where your psi n inside the K is the exact eigenstate of the nth excited state in of a one-dimensional harmonic oscillator. So this question is very big first, then is very overwhelming because of this many equation and all. But see, again, this is a particle in a one-dimensional harmonic oscillator, and your perturbation is epsilon, the electric field. So you all already know the Hamiltonian, right? So I'll write it here. Your Hamiltonian is given as minus h cut square by 2m d square by dx square plus half m omega square x square q epsilon x. Okay, so this is your Hamiltonian is given. If you remember, okay, this is already given. So okay, let us start from here. Now what we can do to get the exact expression of the energy so that we don't have to do any integration. See, first order correction is given, right? This is perturbation. This is your perturbation that is understandable, right? HP, and this is your H naught. See, what we can do, we can change the variable. That is, we'll take an arbitrary y, another axis, which is x minus q epsilon by m omega square. So you can say that where did you get this and why are you doing this? I will say you that I already know the solution. That's why uh, I'm solving it like that. It is actually hard for anyone to do it in the first go. But if you have already think like that in that pathway, then it is easy. What one would do, one would try to solve the Hamiltonian that what we have done, that first order correction. One had to remember the size zero for a harmonic oscillator. But we're not doing that. We bypass that. That is one we are going to get dy is going to be dx, right? And again dy dy is dy dx, and similarly dy dy d2 by dy square is actually going to be d2 by dx square, right? So we can, I'm going to actually change, I'm going to write it in terms of y. And again, we have x is equal to y plus q epsilon by m omega square. So your x square is going to be y square plus q square epsilon square m square over 4 plus 2 q epsilon y m omega square. So we'll put these values here. Why I am doing this? I am doing this because your perturbation have a x dependent part. I can't write that this is n into n plus half into h nu and qex, because x is already a variable, so you need to do an integration if you want to have x in your, as your, means as x is there, so you need to integrate that part, but I don't want to integrate. What I want to do, that without the integration how to do that, I am showing you. So I have just changed the variables in terms of y, another direction, another arbitrary coordinate you can say, and I will put the values here. So now my modified Hamiltonian. Okay, so this is the modified Hamiltonian. So minus h cut a square by 2m. So it will become d by dy square. Then it is half omega square x square. I will change the values here. Y square plus q square epsilon square m square omega 4 plus 2q epsilon y. Hmm. Okay. Actually, I'm changing the thing that this is going to be plus. Why I have done because I didn't say that I know the solution. I have a upper hand right now, but just see, you can have an idea how to do this, right? Minus, and again you have q epsilon. If not, then you have to use this. So ultimately, you are going to get minus h cut square by 2m d2 by dy square plus half m omega square y square plus half. Now you will see what I am trying to do. Okay. From here, this is cut, right? This is q square by 2m omega square. Here it is minus 1, so I'll write these terms first. Minus q square epsilon square by m omega square. Out of this, now you see this is the unperturbed Hamiltonian for y, right? And see, here is no dependence on variable, right? X or y. So this is your perturbation, right? So you can also write your energy is going to be, let me write it. So your energy is your unperturbed plus your perturbed, right? That lambda E1, right? Here is your, that perturbation part is here. This can be written So the first part, energy can be written n into half h nu, right? This is for unperturbed harmonic oscillator. This is the energy for an inner state minus we are going to get q square epsilon square by m omega square. So this is your expression for the energy. If I so this perturbation has an h dependence, that is why I can, okay. So that's one thing. Okay. If one wants to do by integration, they can do it again, but you want again psi zero and those things, right? So this is one of the process you can use. But this is actually, to be honest, a tricky one because one need to know that which exact variable you want to use, what do you want to change there, and then only you can do it. Now next, the question is calculate the fast non-zero correction to the energy, treating QEX as the perturbation and compare it with the exact result obtained in one. Okay, so see, now we are doing for the second, and this one was for the fast non-zero perturbation. See, your fast order correction to the energy, or you can say your lambda is there, but that is lambda psi n zero. Now it will be q u epsilon x psi n zero. Now you see, this part is anti-symmetric, right? And both are psi n zero. Now if psi n zero is symmetric, and there could be two cases anti-symmetric. What if this, then the integral is symmetric, anti-symmetric is anti-symmetric. Anti-symmetric, anti-symmetric, symmetric into anti-symmetric. That means anti-symmetric, anti-symmetric, anti-symmetric. That is also anti-symmetric in this case also. So this is, and you already know that integral of anti-symmetric antisymmetry functions. Inside, you can say uh, antisymmetric function is zero in a symmetric boundary. Right, because here your limits are minus infinity to plus infinity for a SHO, right? Simple harmonic oscillator. So no matter what, your first order energy correction is going to be zero. So we need to find the first non-zero correction, right? So for first order correction, we are not going to get anything because it is going to give us zero. What about second correction to the energy that is given by lambda square n2, right? So that is actually your. So let us first uh, get this part, huh? Then we will consider about the lambda square. So this is nothing but m equals to 0 not to the power n, and m will go to the value of 0. We have psi m 0th, your QEX psi n 0th divided by En 0th minus Em 0th. Okay, so see here your m can't be equal to n, but m can be anything, right? Other than n. So for the first case, so it could be like anything is coming, then we are taking one case where it is n plus 1. I'll take this as outside, right? It is x psi n 0, and see m can't be n, so the next term would have been psi n minus 1 x psi n 0, right? Okay, this is also 0th term will be the order. And next again, there could be this many possibilities, obviously. And modulus square, this is En 0 minus En plus 1 0, there it is En 0 minus En minus 1 0. Okay. So M can be anything, right? For this first case, it is M is N plus 1, and this part is M is N minus 1. Now omitting the higher order terms in En2, we can actually write here En2 as, so we are ignoring that part. So if we ignore, then we can erase, right? So we can write why we are ignoring, because we are finding the first non-zero correction or first non-zero perturbation, right? Second non-zero perturbation could one can also find by adding more terms which I have written. Firstly, there is this term, it is En minus En minus 1, then again now in question itself it is given this, see this relationship. So the first one is N plus 1 root over h cut by 2m omega. So the first one is root over n plus 1 h cut by 2m omega. Yes. And then we need to take a square of that. What about the energy difference between, suppose this is one part of dn0, this is minus 1 0, and this is n0 n plus 1. So you can see energy order is like this. So this is n plus 1 half into h omega, or you can say h naught, h nu. What about this? This is n plus half plus 1, n plus 1 plus half, right? Something like that, h nu. This is n minus half, h nu, right? So the gap is, for the first case, En 0 minus En plus 1 0 is h nu is common, n plus half minus n minus 1 minus half h nu. That is n cut half cut minus h nu. First is minus h. Then the second part. And you can guess this is going to be h nu, right? E n naught minus a n minus 1 is going to give you h nu. The gap is h nu. Now this is root n h cut by 2m. squared by 2m omega square of that. We are omitting the other terms, don't forget that. We are going to get something n plus 1. Okay, this is minus sign is there, h nu is there, plus n by h nu, and we are also going to take h cut over 2m omega outside, which is nothing but q epsilon h cut 2mw into h nu. Hmm. Is n minus 1 is going to give you minus q e h 2m into 2 pi into minus I've taken, and h nu is 2 pi omega, right? Sorry, omega is 2 pi nu. So nu is omega by 2 pi. So I'll just convert these two things. Oh my god, where did it go? Oh my god, I need to write it again. Oh my god. Okay, no worries. We got um, there is some problem. Okay, we come back and modulus the whole square, and then it was something like I was showing you the energy gaps. It is En 0, this is En plus 1 0, this is En minus 1 0. So energy will increase in this way. The energy gap one needs to understand, this is going to be h nu. These are going to be h nu, but En naught minus En plus 1 naught is going to be minus h nu. Why? Because this is n plus 1, n plus half in terms of h nu, and this is n plus 1 plus half h nu, and this is n minus 1 plus h nu, right? So again, n naught minus n minus 1 naught is going to be h nu plus. So this is minus h nu plus, it was root n h squared by 2m omega squared by h nu. When we take some terms common, we'll see give us n minus 1 is minus q epsilon. So I was saying that your omega is 2 pi nu. So your nu is omega by 2 pi h into omega into 2 pi, and again h cut is h by 2 pi, and here you have 2m omega. So h gone. Okay, h gone. What other terms would be gone? We can say 2 pi gone. Okay, so we have, am I writing it correctly? Okay, see, I have done a mistake again. So QEX was inside this, right? QEX was inside this, so it should have been QE square. So minus Q square epsilon square by 2m omega square. See, this is your EN2, right? And check what is the, this was your first non-zero correction, okay? And see here. Okay, I have done another mistake. It should have been 2, because here it is plus half q square e square by m omega square, and here it is minus q square e square. So minus and plus, so it is minus 1. Here is plus half, so it should be minus half, right? So so you can see that this is actually your first non-zero. See, your En2 actually consists of higher order terms also. So I should write it as minus q square by 2m omega square plus other terms are also there. Okay. So this is the first non-zero perturbation, and this exactly, if we compare it with the exact result of it, so it is actually the exact result. Okay, the exact that perturbation. I hope you have understood this, and now we'll move on to the next problem, which is a small step in the potential energy is introduced. The question is from Atkins. A small step in the potential energy is introduced in one dimensional square well problem in this figure. So we need to write a general expression for the first order correction to the ground state energy and evaluate the energy correction for A is equal to L by 10. So the blip in the potential occupies the central 10% of the wall with N equals to 1. It's better we should go with the nth. So we'll try to get first the correction related to this in this En0. Sorry, that is we know already given sin 0 perturbation. Here perturbation, see your sin 0 is what here? Sin 0 is 2 by L sin n pi x by L. Okay. What is your perturbation area? You can see your perturbation is actually constant, that is epsilon, and that is also from, you can say, L by 2 minus A by 2 to L by 2 plus A by 2 in this region, or 0 elsewhere. You got my point? I should write it in mathematical form. When x is between this. Then there is the perturbation epsilon, which is constant. See, it is not is dependent. So your perturbation in that part, so your integral is going to be inside, you can say, now if I write it in integral form, the integral would be from L by 2 minus A by 2. It's better to write L minus A by 2 to L plus A by 2, 2 by L sine square n pi x by L epsilon dx. And you already know epsilon is constant, so you can take this thing outside. This is L minus A by 2, this is L plus A by 2, and actually you can take these two inside and make this 2 sine square n pi x to 1 minus cos 2n pi x by L, right? Dx. So you have epsilon by L minus A by 2 to L plus A by 2 dx minus epsilon by L minus A by 2 to L plus A by 2 cos 2n pi x by L dx. Okay, so I'll go to the next page. So we have epsilon by L into dx, integration of dx is x, which is L plus A by 2 to L minus A by 2, and here I have epsilon by L, integration of cos 2n pi x by L, I will get L by 2n pi, L by 2n pi, right? And sine 2n pi x by L as integration, and again it is from L plus A by 2 to L minus A by 2. So first I'm going to get minus A by 2. Then I have epsilon by 2 n pi, L got cut. Then I have sine 2 n pi into L plus A by 2L minus sine 2 n pi into L minus A by 2L. So this is actually tricky Epsilon by A, you can see not this part, but the another plus L plus A minus L plus A, L is gone. So 2A, and you are going to get 2A, but 2 cards, so you are going to get A epsilon by L. What about this part? This is epsilon by 2n pi sine 2 card. Now we are going to get n pi L n pi A by L. See, that doesn't make any sense. Let me erase it and write it in another format maybe. N pi L plus A by L. See, everything is constant other than this n can be varied, right? L is constant. Now, if n can be any integer, and for any integer, acha, this is also what I thought it is not. So let me correct it. I thought it in a different manner. So no, that is not going to happen. N pi L by L is gone. Now it is N pi A. Okay, N pi A by L. Same here. Sine N pi L by L minus N pi A by L. And you can see L by L means N pi. And you already know what this is, L by 2n pi. So this is actually your sine A plus B minus sine A minus B format, which is 2 sine B cos A. Okay, so we are also going to get something like that. So we are going to get 2 sine B. B is n pi A by L into cos n pi. Okay, I'm going to get something like this for. So this is your E nth state first order correction. And if we can simplify it a little, then we will erase these two, right? And what else we can do? Well, nothing much, right? So we need to, they have said to calculate for the first part A, write a general expression for the first order correction to the ground state energy E10. So E10 will be A epsilon by L minus n by 0 into pi, that doesn't Sine 0, right? Cos 0. So this is going to be 0. So it is A epsilon by L for the first part. Okay. Firstly, yeah, that is actually, I also didn't thought about that. But see the question. The ground state energy can't be, the correction is E01. See, I was thinking like it's sine 0, 0 by 0, this is undefined, right? So for a particle in a box, in a box, n start from, n is not equals to 0, n starts from 1, 2, 3 and all, right? So actually I should write undefined, right? But if anyone say that the correction towards so that would be sine pi a by L into cos pi. Again, cos pi is minus 1. So a epsilon by L minus epsilon by pi, it is plus sine pi a by L. Okay. So this is actually E correction first order. Actually, obviously, there should be lambda, this should be there, right? But they actually wants to know what is E11 or E10, right? Correction to energy. So, and what else is given? The second question, evaluate the energy correction. Uh, Central 10%. So L by 10. A is equal to L by 10. So we put L by 10 here. L by 10 into epsilon by L. Epsilon by pi sine pi into L by L10. LL gone, LL gone. This is epsilon by 10 plus epsilon by pi sine pi by 10. So I would encourage you to do this yourself, the calculation. Maybe you can use the calculator and do it. And acha, as I am doing, let me solve it fully. So actually we are getting something epsilon by 0.409. Okay, overall. So this is your correction to the energy. Okay, now we have another question. So this is the maybe the last question we can solve, and then the next I was planning to solve some variation theorem problems. I'll share with you at the end of this problem, and we can solve it on the next day, I guess. So we normally think of one dimensional as well as being horizontal. So we normally think the question says this is also from Atkins. We normally think of the one dimensional whale as being horizontal. Suppose it is vertical, then the potential energy of the particle depends on the x because of the presence of the gravitational field. So it says that now think your x is in this direction. Okay, here your v is infinity and this is your 0 and this is your a. Right? This is what they want us to say. They are saying actually. Here is b equals to infinity. Here b equals to 0, right? So first your psi 0 or psi n at 0 is 2 by L sin n pi x by n. Calculate the first order correction to the 0 point energy. So 0 point energy again is dependent on 0 0. So it will be 2 by L sine 0 point not 0 but 1, right? There is nothing called n equals to 0 in so that is coming from the boundary condition itself. If you remember the derivation of the wave function for a particle in a box, and so this is this, and normally you know the energy is n square e square by 8 ml square. Now they are saying that a gravitational thing, so Hamiltonian, let me write it down, minus h part square by 2m d square by dx square is being attached with now what it has been. So, so gravitation, right? So which is mgh. See, depends on the height as mgh, the energy of the particle. So that potential is added mgh. So this is your unperturbed part, and this is now your perturbation. Okay, small perturbation. Calculate it and evaluate for a electron in the box. In the box, in a box on the surface of Earth. So, firstly, G is 9.81 in the surface of the Earth, right? And mass of the electron is 9.11 into 10 to the power minus 31 kg. Okay. Now we need to calculate the perturbation, that is firstly the E1 1/8, that is psi 1 0 mgx psi 1 0. Okay, so it is, so now see, if you remember the problem we were doing for the perturbation, first order perturbation for a simple harmonic oscillator, there we have said that perturbation, first order perturbation correction is zero. Why? Because it was inside a symmetrical boundary, minus infinity to plus infinity. But now it is for a particle in a box, it is from 0 to L, so it is not 0. We don't know yet. We have to solve it and then we can say the psi 1, they are going to give 2 by L, uh, sine square pi x by L, x and mg is there, okay? Dx. I should write dx in here. Okay, so now let us solve this. So this is nothing but mg by L 0 to L x 1 minus cos 2 pi x by L dx, right? So here we are going to get mg 0 to L x dx minus mg by L 0 to L cos 2 pi x by L dx. So mg by L overall common let me take. So that is x square by 2 going from L to 0, and here it will give you minus L by 2 pi into sine 2 pi x by L going from L to 0. Now mg by L outside, here you are going to get L square by 2, right? Minus 0. Oh, and then here you are going to get L by 2 pi into sine 2 pi. Other part is 0, as you can see, sine 0, but L 2 pi, that is also going to be 0. So you are going to get your 1 1 as mg by L into L square by 2, which is nothing but mg L half this. So they are asking that we have already calculated the first order correction, right? See, actually this is not the first order correction. I am saying again and again we need to multiply with lambda. But in generally from the so actually the question is something like that. Okay. So they actually want us to find out this, but you should always remember the first order correction. First order correction to the energy is lambda E for particles in a box. That's why I take this for ground state PIV. Now the energy of the particle depends as height as mgh. So that's all. Now this is your perturbation. Not the perturbation, but E11. After that, I had planned to solve the variational theorem problems, the way the actually the assignment problems, and then I had some numerical problem. So I will share the notes with you and read this one and we can discuss it actually on the next class. We'll discuss it in the next. So you can try to solve it by yourself. I have taken this from internet. I don't remember which exact PDF file I have taken it from, but I have to confess these questions I have not made myself. I have taken it from internet. So we'll solve it together maybe on the next time. Till then, uh, so well, I have written this because I guess we need to use this formula somewhere while solving those problems. So with that, we'll stop for today. We'll meet on the next day. I hope solving this numerical is helping you by somewhere or the other. Please let me know if you are finding it difficult to solve or you have some suggestions uh, how to maybe if we can improve these live sessions. There are only two live sessions are left where I will try to solve this variational theorem problem as well as um, some hybridization and some bonding questions. Uh, Also, I will try to take an extra class because this is not due to that oh, solve many other questions, but the thing is that I to meet my PMRF criteria that hour per year I need to take 50 hours of TO duty, but in this year I have already taken if I take another two regular live discussion session, then it will be 48. So I would like to take one extra 2 hour course. I'll discuss with the PMRF who are the NPTEL PMRF team who are handling this if they can permit me to have one extra class. So there I can we can discuss some more problem or we can discuss the overview of the whole class or whole lectures from lecture 1 to maybe I think there will be 62 lectures. So we can discuss that and we can discuss some important formulas, what to remember, what not to do. That we can do in that week 13 video. With that, let me stop today. I hope you have found this useful. Please let me know of your suggestions. Thank you.